My name is François Schmidt. I'm a student at the BSc Honors in Data Science and Artificial Intelligence at IIT Guwahati. This is my Term 8 project. What we are trying to answer here is, does machine learning beat the credit scorecard? So we are looking at the way banks allocate loans, one of the metrics being profitability, and we are comparing the result of a small neural network with a couple of trees, namely XGBoost and LightGBM. So the task is to estimate the probability that a loan applicant defaults using only the information that's available on the day of application. The reason why it's important is that if we look at the final file that is provided by Kaggle, we have a lot of data that shows whether the loan was repaid or not. So we have to exclude that, but we'll come back on that. So the discrimination is trying to assess whether the model ranks bad borrowers above good ones. Namely, we're looking at the around ROC curve, and we compare distributions through KS. We do some calibration, and we look at the profit, which is obviously the benchmark for banks to assess the successful of their models. So we put together reproducible Python stack. I just on my computer here. Language is Python 3.13. We use Pandas, NumPy, Kaggle Hub. Scikit-learn as library, where we get also XGBoost, LightGBM, SciPy. The workflow is in Jupyter. We have some VS Code, GitHub, where everything is posted, the LaTeX report as required. And let's look at the data. So the Lending Club has provided on Kaggle some personal loan data that we need to engineer against leakage. So we have a number of small unsecured loans. They rank from $500 to $35,000. Median one is $10,000. Repayment is $342 a month. We have the FICO credit score, which is the credit scoring in the USA. It gives an area of inputs that are used to determine the credit score of an applicant. So we have also in this data the purpose of the loan, the housing situation, and the grades that are given by FICO, but we'll come back to that because likewise, as I'm stating here, the leakage filter is quite important. So we trained the data on the 2007 to 2013 period. We did the calibration on 2014, testing on 2015, and then at the very end, I've also run that against some Taiwan data. So the Lending Club is in the USA, but it was interesting to run that just somewhere else to see how that works. I've got here some screenshot of my work environment. You can see the tabs here. I might as well go to the VS Code. So we have the pipeline here that's showing, how the code runs. We see Taiwan at the end to do some final testing. We have the various models here. XGBoost, LightGBM. It's just fairly standard calls. The various metrics that we use are described here. We have the scorecard, and obviously I would like to show a brief insight into the data itself. So the data itself is read from the Kaggle website, and if we do a quick insight into the data, this is what we get. So let's just run this. We have a number of, so that has been transposed because otherwise we have too many features, so we have put the features here in line and the different borrowers in columns. So we have tax lien, we have mortgage account, whether they have or not, whether they were charged off within 12 months. So charge off is something that we need to exclude. So this is basically the whole data that's provided by Kaggle. So let's go back to the presentation here. So as I was saying, we have one pipeline, 4 models, identical information across the models. That's where it gets interesting. We have 23 origination time fields that we kept. We can't use anything that is inserted in the data after the loan has started, because if people pay until the end, obviously we know that the loan is repaid and not something that would appear. Our baseline is the WE scorecard, and here I'm showing all the columns that we have discarded. So as an indication, if we have something like the collection recovery fee, it means that the loan has not been repaid. We can't really put that into the model. So yeah, another screenshot of the code itself. So how do we do the discrimination? We look at the AUC and the result of the KS, which is the Kolmogorov-Smirnov distance. This maximum distance between the two score distributions. So both ignore whether the probability of default values are right. We look at just the distribution. We do some calibration, look at metrics for that, the bar, which is the mean squared error of the probability, the average gap between the predicted probability of defaults and the observed default rate over the various bins, knowing that every borrower is put into a bin. Then we look at the realized profit per 1,000 applicants across accept, reject cutoff, the cash flows, which mean that the loan has been paid until the end or not. So once we've run our models, we have sense that the 3 models win. The neural net doesn't do so well compared to the scorecard. So that's expressed here by obviously the scorecard, which is the baseline, and the score of the MLP, the light GBM, and XGBoost. So these p-values are very small, which is interesting because we have a very large number of loans. Statistically decisive. We have 283 over 283,000 test loans. We can see that economically we have 0.85 AUC points, which is not 825 that sometimes is randomly is quoted by the random split studies, but we see that the deep learning is actually not yielding as much as we probably were hoping as a neural network compared to just running some trees. We have here the calibration. The raw model predicts the future. That's what we expect. The raw trees do not work so well, but they are recalibrated, and this is where it becomes useful. So we perform the isotonic calibration. We find out that in 2014 we had a change of regime, so generally more loans defaulting because of some economic turndown. So that's something that we've borne in mind. Yeah, so before the calibration, the scorecard is actually performing better. Here we look at the profits. We find out that if we accept everyone, that loans about $705 per applicant. Bear in mind that the size of the loan is different, but it's just one metrics. The scorecard reject some of the riskiest borrowers. XGBoost rejects more than the scorecard, but if we look at everything, we find out that there is a modest edge. But again, it becomes volumes, so that's why banks may be tempted to use XGBoost. So the models are working better, so XGBoost namely versus the scorecard. But what we have to think about is that in the data that we've kept the grading by the lending club, and if we decide to look beyond that, which is where this study becomes actually interesting, we can do two variants of the model. Variance A, where we drop the grading that is provided by the lending club data and the interest rate, because obviously the lower the creditworthiness of the borrower, the higher the interest rate. And then in the variant B, what we drop at the same time is also the loan amount that is repaid to the installment. Both features are highly correlated. And we run the study again. So we found out that for the variant B, the change is minus 0.021. For XGBoost, 0.022 for like GBM, MLP, small change as well. And for the scorecard obviously performs much worse, because the scorecard really needs the input as in the creditworthiness. So it shows that the other models are actually performing better if we remove some data from the scorecard. So we can do again the same ranking on an independent data set, which is the Taiwan credit card default. So I've shown that in my code that runs. It's working okay. XGBoost works better than the small neural network. So that's confirmed. So it's probably time to draw some conclusions, and we find that the machine learning wins, but not all machine learning. It's mostly the trees, and that's only after calibration. So there's always more that can be done, like rejecting inference, default timing for the survival models, looking at different time periods, because as we've mentioned, we had an economic turndown in 2014 probably, and so on. So that's it for now. Thank you for watching.